Right, so we've found two of the more difficult parts, or two of the more difficult things in our titration curve of acetic acid or ethanoic acid having sodium hydroxide added to it. We've got the initial pH found by finding the concentration of a weak acid, knowing it's pKa. We've found its equivalence point volume by looking at the reaction between sodium hydroxide and ethanoic acid. We've found its half equivalence point and pH by halving that and then looking at the pKa and look at that, are the same. So now we can actually complete the shape of it quite easily. It goes pretty much vertical through here, and this is why if you have an indicator that has a pKa around there, it will change colour in this zone. And then it suddenly starts to head towards a maximum, but never reaches that maximum. And what we're going to do is we're going to try and work out what the pH is of that theoretical maximum, that it will never reach, but it'll get incredibly close to. Here it's just understanding the chemistry. Once this is reacted all the way, then actually all you've got is ethanoate ions, which are alkaline, and you're adding more and more sodium hydroxide to it. So the more sodium hydroxide you add, the closer it gets to being 0.45 moles per litre sodium hydroxide, doesn't it? If I keep adding that stuff, it'll get closer and closer and closer to that concentration, but never quite reach it. Never quite. So we're finding a maximum that we're going to get really, really, really close to eventually. Add 200 mils of this stuff and sure it'll probably be 0.450 moles per litre, but that's not reality. You'd add probably an extra 3 or 4 mils and stop. So we need to find what this theoretical maximum is. It's actually really straightforward to work out. What we're looking at is, if that's what in theory it's going to end up being, then we just have to find the pH of that strong base. So we have to remind ourselves how to do that. So that strong base has got 1 hydroxide ion per mole of sodium hydroxide. So it's got 1 mole of sodium hydroxides for every 1 mole of hydroxides for every 1 mole of sodium hydroxides. It's got 0.450 moles per litre of sodium hydroxides, so it's got the same concentration of OHs. So I actually know at the end I will have this equal to 0.450 moles per litre. Alright, so knowing that it's going to be that concentration, I can use Kw to find out what the hydronium would be. Alternatively, I could find the POH and go 14 minus that, whichever way works better for you. I'm going to go the way that we're meant to, which is this. Hydronium equals Kw, which is 10 to the minus 14, divided by 0.450. I'm going to need one of you to do that for me, please. Okay, and then when I do the negative log of my answer, 13.7. Okay, 13.7. So I have that theoretical value. It won't ever quite reach that, but it will to that many significant figures. So now I've filled in all the key parts to be able to sketch my titration curve. The middle of this steepest part, if this was done to scale, would match up with the pH at the equivalence point. The reason that, but for choosing an indicator, which we're going to get to on Friday, that's about finding any indicator which has a pKa in that pH range where it's very, very steep. Because that means one more drop and it'll change the colour of the indicator. Or one more drop has zero effect on the pH here. Start again. One more drop is going to dramatically move it out of this into here. Okay, so it'll have a dramatic effect on pH without having a dramatic effect on volume. Okay, so we look for indicators that are in the steepest part. So for this one, I'd expect that to be around about 9. So we'd be looking for an indicator like phenolphthalein, which has a pKa around about 9. But we'll do that in more depth on Friday or on Monday. So now we've covered the key points of here, and we could estimate a range for our pH, which would make it so we could choose a suitable indicator for this titration if we didn't know the concentration of one of these. Any questions on that?